Alright, hey everyone, welcome back to 3 Deviations. In today's video, we've got a fairly self-explanatory video, which is the limit of a vector function. Now, we discussed the idea of a vector function, how we can have 3 parameters, i.e. our 3 coordinate positions, modeled by some parameter t. So this is, of course, parametric equations taken to the next level, as one might imagine. So now we have learned about how these vector functions work, and similar to parametric equations, we want to learn how we can do calculus with these vector functions. So naturally, the first place to go to is to discuss the limit, because the limit is one of the most fundamental ideas of calculus. So we want to discuss how to take a limit of vector functions, and it turns out it's quite an easy task. So if I want to take the limit as t approaches a of r of t, I can just take the limit of each of the components. So I take the limit as t approaches a of f of t, then I take the limit as t approaches a of g of t, and then I take the limit as t approaches a of h of t. Now, as you might see, these are very similar to real-valued functions, and this is also very similar to how we discussed the domain of the vector function, how essentially we just need to look at the domains of all of the components that we have. So it is really a fairly easy task that we have, but it is very important because it will guide how we look at derivatives and integrals of vector functions, which are incredibly important, especially in the world of physics. So we'll finish off this video by trying an example. So we will take the limit as t approaches 0 of r of t. Not very helpful because I haven't told you what r of t is, but here we go. R of t is equal to 1 plus t cubed for the x component, t e to the negative t for the y component, and sine of t over t for the z component. So we're throwing pretty much all of our elementary functions in. We've got polynomials, we've got exponentials, and we've got our trig functions. All right, now we will go on and try this out. So we will take the limit of the x component. The limit as t approaches 0 of 1 plus t cubed is equal to 1. It's fairly direct substitution. Everybody knows this t will go to 0, so we just are left with the 1. Now we take the limit as t approaches 0 of t e to the negative t, which is, of course, also 0. Well, how do we know this? We know this because even though e to the negative 0 is still going to be real valued, if we take the t that is multiplying us, then we get something that is 0, so we get 0. Then finally, we take the limit as t approaches 0 of sine of t over t. This is one that you might need to go way back into Calculus 1 to remember, that this, or maybe even real analysis if you prove this, so I don't know why you'd be taking multivariable after real analysis though, but anyways, you take the limit as t approaches 0 of sine of t over t. That's a limit from Calc 1 that you need to remember, because that limit actually is 1 despite what you might think, because it gives an indeterminate form. Anyways, that's all fairly unimportant. So we can plug this back in to our vector equation. We get the limit as t approaches 0 of r of t is equal to 1, 0, 1. Now graphically, we can see what this looks like. So here we have our vector function graphed. The domain of this vector function is t equals 0, comma 10. But because the function is asymptotic, it goes all the way off. So essentially what we're looking at is this point. I want to find what we approach, so we go closer into here, and it looks like we're up. Looks like we're up about 1, and we're also over about 1, so that looks right, and there's no variation along this axis here. It's only on the x and z axis. All right, thanks for watching today's video. In the next video, we're going to make the natural step to talk about derivatives of vector functions. See you then. Thanks for watching.